and welcome back to Calculus 1. So today we are talking about infinite limits. That's going to be 2.4. So infinite limits, and when we're talking about infinite limits, we are looking at the limit where x goes to some finite number c, a, of a function, and we are looking for the answer to be either positive or negative infinity. So this is what we are looking for. A quick example of this would be, say, limit of ln x as x approaches 0 from the right, and you know that's negative infinity, because when you look at the graph of ln x, you see that the approach from the right gives you, as you go closer to 0, gives you negative infinity as the answer. We know that the solution to the limit from last class is technically the y value that you get to compute. So in this way, as the x coordinate is moving towards 0, the y coordinate, the solution, is going on to infinity. Another example of this would be, let's say, a limit x goes to, let's say, 3 of 1 over x minus 3 Actually, I don't like that one. X minus 3 squared. Now you see that this is shifted, depending on how well you know graphing, but 1 over x squared graphs like that. So our problem is shifted 3 units to the right. So we are going to have a vertical asymptote at 3, and have our graph the same shape. And now we can use our approach from left and approach from right. So approach from the left would be limit x approaches 3 minus, which means from the left, of 1 over x minus 3 squared, and we see that's positive infinity. You can just write infinity, you don't need a plus. And then the blue approach, which is from the right, is limit x approaches 3 plus, from the right, 1 over x minus 3 squared, also gives us positive infinity. And then by the theorem that we studied last class, if you have both approach from the left and approach from the right give you the same value, same answer, right? The answer for the overall limit, x approaches 3 from both sides simultaneously, would give you, in this case, positive infinity as the answer. And that's the end of the problem. So we call this infinite limits because the limit, the answer, is one of the infinities, either positive infinity or the negative infinity. Now we have to be a little bit careful if we are talking about limit x goes to 0 for 1 over x. Graphs really save your life in these situations, so you should always draw a graph and try to draw conclusions from the graph. So as you draw your graph, you take a look at your approach from the left, which is the limit as x goes to 0 minus, because it's from the left, and you quickly see that the answer is negative infinity. For the blue approach from the right, you have limit 1 over x, x goes to 0 plus, will give you positive infinity as the answer. So what's the total derivative? The overall derivative, limit 1 over x as x goes to 0 from both sides, does not exist. Why? They're different. They don't match. So the theorem from last class said if these two have the same values, the overall limit is that value. If they have different values, then the overall limit does not exist. So if you look at the previous example, they match, therefore the overall limit is that value. This one was actually only one-sided limit. I only looked for the limit from the right because there is no function to the left of 0. So you can't look for the approach from the left. So one-sided limit or two-sided limits, we have the theorem to deal with those. Infinite limits provide you with this does not exist on the end. Now you did the class prep. So what is the mathematical concept, very important mathematical concept that we can define using these limits? Which one? Vertical asymptote. Very good. Now that is crucial for this section. Vertical asymptote, usually abbreviated by VA. And the definition for the vertical asymptote is that if the limit x goes to a value c, minus of f of x is equal to positive negative infinity, or the limit x goes to c plus of f of x is equal to plus minus infinity, then there is a vertical asymptote at x equals c. So limit as x goes to 0 for 1 over x from the left is equal to negative infinity, which implies vertical asymptote at x equals 0, which is always the value that you are approaching. Make sure you use the correct mathematical notation. VA equals 0 is just a garbage that has no information. That's meaningless. So don't write that. The equation of the vertical line is x equals a value. So x equals 0, x equals 3, x equals 5. That's the equation of the line. All right. Also know that the limit x goes to 0 for 1 over x squared is equal to positive infinity. Therefore, again, vertical asymptote at x equals to 0. So, oh my God, come on, leave me alone. So what else do we have for these vertical asymptotes? Does anyone remember from your pre-calculus course the procedure to find vertical asymptotes? How do you find vertical asymptotes? Yes. What do you mean, is it the denominator? Denominator equal to 0. So if we have f of x equals to x plus 5 over x squared minus 25, how many vertical asymptotes do we have? Just talk. Two? One? Two? Say 2, say 2, 0 and 5. Say 2. You say 1. Why do you say 1? Everyone else is 2. So are you that much better than everyone else?
You can factor it out of the x plus 5, x minus 5, and then there'll be a whole at
Ooh.
5, so that makes the whole.
Shiny. Yeah. It's one asymptote. He knows it. So the good old pre-calculus set denominator equal to 0 will now give us candidates. And we have the definition to run and check each one of those values. So here's what we're going to do. X squared minus 25 equal to 0. X equals plus minus 5. We have two possible asymptotes. So what this is two possible asymptotes. That's all we have from good old pre-calc. See, in pre-calc, we kind of stay away from these types of problems because you don't have tools to check. Because the tool to check is the limit. So now we say, all right, let me see. Limit x goes to 5. Is this a vertical asymptote? We have our function. The way to solve this is, we know from last class, like factor. These guys cancel. We are left with limit x goes to 5, 1 over x minus 5. Now we know how to graph 1 over x minus 5. It's just 1 over x shifted 5 units to the right. That's cheap and easy. So it looks like this. And we already see from the picture that there is a vertical asymptote at 5. But you can also do the left limit, right limit. So the limit x approaches x approaches positive 5. For 1 over, from the left is equal to negative infinity. So that's good enough to know that there is a vertical asymptote. So vertical asymptote at x equals to 5 confirmed. Now we run the limit for the second asymptote candidate, which is negative 5. We end up with the same 1 over x minus 5. And you get negative 1 over 10 when you plug in 5 on that one. This is supposed to be negative 5 here. So 1 over 10, negative 1 over 10. So now that's not infinity. So no vertical asymptote at x equals to -5. And as you said, we have the open circle there. So if I am to graph this function, I will draw the vertical asymptote at +5, and then at -5, and -1/10, I have the open circle. So the function will go like this. So you see that there's only one vertical asymptote. Now I'm going to encourage you to actually use your calculators or your cell phones and graph this to see. Now graph the original problem, obviously. The x plus 5 divided by, make sure you use correct parentheses, and you will see that you will get this graph. And then if you zoom in at the value for -5, you will see a missing pixel there. So just use your calculators. Those of you with correct technology, you can download those calculators onto as an app. Yeah. You zoom in around 5, you'll see a missing pixel. So you can see only one, if you graph it correctly using the parentheses, so it has to be x plus 5 in parentheses divided by parentheses around x squared minus 25. If you did it correctly, you will see only one vertical asymptote. And now per syllabus, you know that there is no graphing calculator on the exam. So you should brush up on these graphing skills for basic functions, because 1 over x minus 5 is basic function. It's just 1 over x that is shifted 5 to the right. And you can see basic 1 over x shifted 5 to the right. And our calculations here show that at -5, since we don't have infinity, we don't have, that's the calculus part you learned. So this is now taking what you learned in pre-calculus to the next level, where you are learning concepts, mathematical concepts, more in depth, and you're upgrading. So in pre-calculus, you will learn that you are setting denominator equal to 0, and you get these asymptotes, and that's it. But the problems were tailored so that these situations would not arise. Now in calculus, when we have the actual definition of the vertical asymptote, we can put whatever. So whether it's a tangent, or ln, or 1 over x, it doesn't matter what it is. Once you do the limit, you will either get infinity or you will get the finite value. What you are learning is that the finite values are open circles, because those are still 0 in the denominator, so you can't have those values. And if you get infinity, like we had in a line above, then it is an asymptote, because it satisfies the definition. So, believe it or not, that's it. I hope you're not disappointed, but that's 2.4. You are learning that infinite limits will give you either positive or negative infinity as the answer. If the positive and negative infinity don't match for the left and right approach, then the answer does not exist. And then the major application for this math-wise is definition for vertical asymptote, where if you get positive or negative infinity, it is a vertical asymptote. If you are getting the finite value, it is the open circle on the graph. Now the question is, pushing forward beyond math and math rules, does this have application? Obviously, everything in mathematics has application. And especially now in calculus, all of our technology and business and everything is run by calculus. So one of the cool examples would be to actually use this concept and to understand why, when you short circuit the outlet, why is there a little explosion there? So if you look at the formula for current, it is the voltage divided by resistance. And the voltage is, let's say, 110 volts in the outlet divided by resistance. When you plug something into the outlet, resistance could be, let's say, I don't know, 55 ohms. And if the resistance is 55 ohms, you get the 2 amp. So your chargers for cell phones are usually 1 amp or 2 amp, depending on whether it's a fast charging or slower charging, for your computers and so on. So this particular resistance comes from the coil, which is a lot of wires that are winded, and then that reduces the voltage and so on. So you scale down 110 to smaller. So if you want to study electrical engineering, you can go and learn a lot of cool stuff. But what the interesting part is that if you short circuit the two terminals in the outlet, this resistance goes to 0. So now you have a problem which says limit R goes to 0 for 110 divided by R. Now resistance can only be positive value, so technically the graph looks like this. Which is because you can see that this graph is equivalent to 1 over x, and you know how 1 over x graphs. So now what you see is that as you are approaching 0, the answer to this goes to infinity. So as resistance goes to 0, current goes to infinity. So it's no longer 1 amp or 2 amps, it is trying to reach infinity. And in physics, we learned the formula where the current is proportional to temperature. They're directly proportional. So the more the current, more the temperature. So to understand physics, to understand engineering, to understand all of the concepts that are coming on later, the more calculus you know and the more you relate the concepts we're talking about to physical things, the better off you will be in later coursework. So, anyone can learn calculus mechanically. You see a problem, you know the steps, like monkey sees, monkey do. But the idea is, if you really want to be an engineer and have contribution and build stuff, you have to actually integrate these concepts into what they actually are in the nature. So that was one of the applications, let's say, for there's more, obviously, but that's it. All right, I think that's it for 2.4. We're going to say bye to the stream and then restart for 2.5.